morning. This is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. We started discussing one subject called Applied Thermodynamics for 6th semester Mechanical Engineering students. And in this, we were discussing about refrigeration systems, refrigeration cycles. And we have seen that vapor compression refrigeration cycle, we have analyzed it, and before that we have seen reversal Carnot cycle and we have analyzed it, and now in the last class we have seen air standard refrigeration cycle or reversal Brayton cycle, or sometimes called as a Bell-Coleman cycle. And in today's class we'll discuss some problems based on the analysis of this air refrigeration cycle. Now the first problem is like this. A Bell-Coleman refrigeration refrigerator operates between pressure limits 1 bar and 8 bar. Air is drawn from the cold chamber at 9 degrees centigrade and compressed, and then it is cooled to 29 degrees centigrade before entering the expansion cylinder. The expansion and compression follows the law PV power 1.35 equal to constant. Calculate the theoretical COP of the system. For air, you can take gamma as 1.4 and CP, specific heat at constant pressure, is equal to 1.003 kilojoule per kg Kelvin. Now, how to solve this problem? We have to find here what is the COP of the system. So for COP of the system, we need two things. One is the refrigeration effect that is produced, and the other one is the work required for producing that refrigeration effect. And if you see here, this diagram is representing this Bell-Coleman refrigeration cycle or reversed Brayton cycle. Now here from 1 to 2, it is expansion process. From 2 to 3, it is absorption of heat from the cold space, and 3 to 4 is a compression process, and 4 to 1 is a heat rejection to the cooling space, to the cooling heat exchanger. So here from at this point we are absorbing heat from the cooling space, and here we are giving heat to the surroundings through via media of a water cooler. Now, what are the pressure limits that are being talked about here? So, one is 1 bar and other one is 8 bar. So, what are these pressures? So, here as we have already discussed, the heat absorption and heat rejection is happening at a constant pressure. So the pressure at which the refrigeration is happening is the low pressure, that is 1 bar, and the pressure at which the heat rejection is happening to the surroundings is high pressure, that is 8 bar. So P1 is 8 bar, P2 is 1 bar. So this is about the pressures. Now what about the temperatures given? So the air is drawn from the cold chamber. Okay, the air is drawn from the cold chamber at 9 degrees centigrade. So what is the cold chamber here? So this is the cold chamber. So from here the air is taken at 9 degrees centigrade. So at 9 degrees centigrade, the air is entering the compressor and it is compressed to a temperature called T4. So T3 is 9 degrees centigrade, T4 we have to calculate, and then what is happening? And then it is cooled to 29 degrees centigrade. So T1 is 29 degrees centigrade. So the air is taken into the compressor at 9 degrees centigrade it is compressed in the compressor and it is then cooled in the water cooler and it is supplied to the expander at 29 degrees centigrade. Now here, what is the significance of this this law given? So it is stating that the expansion and compression processes are not isentropic process, they are polytropic process. If it is an isentropic process, then it should follow PV power gamma. If these two are isentropic process, then they should follow PV power gamma equal to constant. But here it is not a isentropic process, but it is a polytropic process. Now, how it affects? This also we have discussed in the previous class. Okay, that we will see in form of a numerical problem in today's class. So the given data, as I already told, P2 is 1 bar, P1 is 8 bar, T3 is 9 degrees centigrade. So 9 degrees centigrade, if I add 273, it will become Kelvin, and that is equal to 282 Kelvin. Now similarly, T1 is equal to 29 degrees centigrade. If I add 273 to it, it is 302 Kelvin. So this is the given data for this problem. So what we have to do? We have to find what is T4 and what is T2 in order to solve this problem. So how to do that? First we will take up T4. So the compression process is happening with this law. It is governed by PV power 1.35 is equal to constant. So the compression process and expansion process are governed by this law. So when this is governed, when these processes are governed by this law, so how to find the temperatures which are not known? We know what is pressure at the inlet of the compressor, that is P2. We know what is the pressure at the outlet of the compressor, that is P1. So if I know what is P1 and P2, I can substitute in this formula and I can find out what is T4. So what are the values of P1 and P2? P1 is 8 bar and P2 is 1 bar to the power of what is N? N is 1.35 minus 1 by 1.35. So it is equal to 8 to the power of 0.35 divided by 1.35. So if I simplify this, it will turn out to be 1.71. So this is the temperature ratio across the compressor. Now I know what is the temperature at the inlet of the compressor. So the temperature at the inlet of the compressor is T3. If I multiply that T3, what is the T3 value? It is nothing but 282 Kelvin into 1.71, and that will give us the value as 482.2 Kelvin. So this is the way we identify the unknowns from the given known values in this kind of problems. So this is the, once again I will repeat, it is a polytropic compression. Why it is polytropic? It is given that PV power 1.35 is equal to constant is the law that is governing the compression process. So since it is a polytropic process, we have to take this relationship for finding the temperature which is not known. Here the temperature at the exit of the compressor is not known, and we have to use the temperature at the inlet of the compressor which is known for finding the unknown value. And here P1 by P2, the pressure ratio is also given. So the P1 is nothing but the pressure at the exit of the compressor, and P2 is the pressure at the inlet of the compressor. So this is a temperature at the exit of the compressor. This is temperature at the inlet of the compressor. the ratio is equal to P1 by P2, the pressure at the exit of the compressor and the pressure at the inlet of the compressor, to the power of n minus 1 by n. Now if I substitute the values in this problem, I can find out what is a T4 value. Now we'll take out the T4 into these known values and find out what is a T2. Now the expansion process is also governed by the same polytropic law. So the PV power 1.35 equal to constant. Now how to find the temperature at the exit of the expander? So for finding the temperature at the exit of the expander, what I have to do? The temperature at the inlet of the expander, the temperature at the exit of the expander, this temperature ratio is equal to the pressure at the inlet of the expander, the pressure at the exit of the expander, this ratio upon n minus 1 by n. So if I substitute again, what is P1? P1 is 8 and P2 is 1. Again I am getting the same value as I got in the previous slide. So what is that here? 8 to the power of 0.35 divided by 1.35. So this is the value which I got previously, and that is equal to 1.71. Now using this, I have to find out what is the temperature at the exit of the expander. Now here this is a known value and this is unknown value. So what I have to do? I know that T1 by T2 is equal to 1.71. Now I want to find T2, so I will cross multiply this, so it will become T1 by 1.71, and this is equal to, what is T1? T1 is 302 divided by 1.71, and that it turns out to be 176.6 Kelvin. So this is the procedure. Now we have calculated the temperatures at the inlet. Now we know the temperatures at the inlet of the compressor, exit of the compressor, inlet of the expander, exit of the expander. So what is the use of this? So what we can do is we can find out what is the heat absorbed in the cooling chamber, the cooling space. What is the heat absorbed from the cooling chamber, and what is the heat rejected to the cooling coils, water coolers. Okay. So how to find that? It is nothing but if I know what is the mass of air circulated per minute, then I can write as mCp delta T. This will give the heat, total heat absorbed and total heat rejected. But here we don't know what is the mass of air supplied. So what I am taking is per kg of air. Per kg of air, what is the amount of heat absorbed in the cooling chamber, or this is the refrigeration effect produced. And for the per kg of air means m is taken as 1. If m is 1, Cp into temperature difference across the cooling chamber or across the cold chamber, not cooling chamber, it is cold space, cold region. So, or refrigerator. So, across the refrigerator, what is the temperature difference? So, that is equal to T3 minus T2. What is T3? T3 is equal to 282 minus T2 is nothing but 176.6. And into the specific heat at constant pressure, if I take, it is 1.003. The value of this is 105.7 kilojoule per kg. Now, I got what is the heat absorbed or the refrigeration effect produced. Now what is the heat rejected in the cooling chamber? Here this is the cooling chamber. Here the air is rejecting heat to the water coolers. Now what is that? Again the same thing, mCp delta T. But here I am finding per kg of air, that means m is equal to 1. So Cp into delta T across the cooling chamber. So what is the temperature difference across the cooling chamber? The highest temperature is T4, the lowest temperature is T1. So it is a Cp into T4 minus T1. So what is T4? T4 is nothing but 482.2 minus what is T1? T1 is nothing but 302 Kelvin. So if I simplify this, I will get this value. Now, if at all these processes, the expansion and compression process, are following the isentropic process. Isentropic process means PV power gamma is equal to constant. If these expansion and compression are following the isentropic process, simply by taking the difference of these two, the heat absorbed and heat rejected, I can get what is the net work done. Since here the expansion and compression process are not following the isentropic process, the difference will not be equal to the work done. Why? Because in the compressor and in the expander, there is a heat rejection to the surroundings. So there is a heat transfer to the surroundings during the compression and during the expansion. If it is isentropic process, then there is no heat rejection or no heat exchange with the surroundings during the compression and expansion process. But here it is a polytropic process. That means there is definitely some heat transfer or heat exchange between the compressor, expander and the surroundings. That is the reason for finding the work done, what I have to do is I have to find the area under this graph. So what is the area under this graph? That I want to find. Now, what is the area under this graph? How to find out that? So if I know what is the work done, okay, work done during the compressor minus work done during the expansion, that will give the net work. Work done during the compression and minus work done during the expansion will give the net work done during this process. Now, this P4 V4 minus P3 V3, that can be replaced by R into T4 minus T3. And similarly, P1 V1 minus P2 V2 can be replaced by R into T1 minus T2. Now, if I substitute my values, I know these values of T4, T3, T1, T2, and I know what is R and I know what is N. If I substitute these values in this, I can find out what is the value of the net work done during the cycle. Now, if I don't know what is R, how to find out? So, R is nothing but Cp minus Cv. Cp is specific heat at constant pressure and Cv is specific heat at constant volume, and gamma is nothing but Cp by Cv. So, I know what is the value of gamma, I know what is the value of Cp and Cv, then I can find out what is the value of R. So, here Cp is known. Cp is nothing but 1.003 and gamma is 1.4. So, from this I can find out what is Cv, that is equal to 1.003. Cp by Cp by 1.4 gamma. So what is Cp value? Cp value is 1.003 value. Now if I subtract this value from 1.003 minus 1.003 by 1.4, this will give me the value of R, the universal gas constant, that is equal to 0.287 kilojoule per kg Kelvin, but it is generally given as 287 joules per kg Kelvin. Now R is known, N is known, T4 is known, T3 is known, T1 is known, T2 is known. If I substitute all these values in this formula, what I can get is what is the net work done during the process. So what is N? N is nothing but 1.35 divided by 1.35 minus 1 into 0.287 into T4. What is T4? 482.2 minus T3 is 282 minus T1 is 302 minus T2 is 176.6. So this is the substitution. If I simplify this, I will get what is the work done. So I know what is the work done, net work done during the cycle. I know what is the refrigeration effect or heat absorbed from the cooling space. If I take the COP formula is nothing but refrigeration effect or heat absorbed in the cooling space divided by the work done. So the 105.7 divided by what is the work done? Work done is 82.8. So it is 82.8. So if I simplify this, I will get what is the COP of the refrigerator given in the problem. So this is a simple problem that we have discussed. And now we will see another problem wherein the expansion and compression process are happening or are governed by the isentropic law. So we will read out the problem. An air refrigeration open system operating between 1 megapascal and 100 kilopascal. So the pressure is 1 megapascal. 1 megapascal means 1000 kilopascal. So highest pressure is 1000 kilopascal. That means P1 is nothing but 1000 kilopascal. And what is the lowest pressure? It is 100 kilopascal. P2 is 100 kilopascal. And it is required to produce a cooling effect of 2000 kilojoule per minute. So in the previous problem, we had calculated what is the refrigeration effect produced per kg of air. Now here in this question, what they have given per minute, what is the refrigeration effect produced? So if I know what is the refrigeration effect per kg of air, and if I know what is the refrigeration effect per minute, I can manipulate and find out what is the mass flow rate of the air through this refrigeration cycle. And what about the temperatures? So the cold chamber, this chamber is maintained, the air is leaving the cold chamber. That means at T3 it is minus 5 degrees centigrade. And the leaving the cooler, the water cooler, it is leaving, that is T1 is equal to 30 degrees centigrade. And we can neglect the losses, clearance in the compressor and expander, and we can find out what is the mass of air circulated per minute, and compressor work, expander work, cycle work, COP, and power in kilowatt per minute. Okay, how much kilowatt power is required for running this cycle, that also we can find out. So as I already told, what is P2? P2 is nothing but P2 is 100 kilopascal. Oh, this is P2. This is P2 is 100 kilopascal and P1 is 1000 kilopascal. Now what is T3? T3 is nothing but minus 5 degrees centigrade. If I add 273 to that, I will get 268 Kelvin. And T1 is 30 degrees centigrade. If I add 273, I will get 303 Kelvin. And already they have given the cooling effect or the refrigeration effect produced, that is equal to 2000 kilojoule per minute. So with the given data, what I have to find? I have to find out what is the work of the compressor, work of the expander, what is the net refrigeration effect produced, what is the COP, what is the power required. So for this again, what I have to do, I have to find out, I know what is T3, I have to find out T4, I know what is T1, I have to find out what is T2. Now here, first thing is I have to find out what is the mass flow rate of the air. For finding the mass flow rate of the air, if I know what is T2 and T3, I can find out what is the refrigeration effect per kg of air, and I also know what is the refrigeration effect per minute. From that I can find out what is the mass flow rate of the air. Now, since it is a isentropic process, N is equal to gamma. So gamma is equal to 1.4. So I know what is T1. T1 is nothing but 303 Kelvin. And what is T2? T2 is I have to find out. So what is P1? P1 is nothing but 1000 kilopascal. And what is P2? It is nothing but 100 kilopascal. And it is 1.4 minus 1 by 1.4. So it is equal to 10 power 0.4 by 1.4, and that is equal to 1.9306. So this is known. If I substitute these values here, I can find out what is a T2 value. So once I know the T2 value, I can substitute that in the refrigeration effect produced, and I can find out what is the mass flow rate of the air. Now, the refrigeration effect per kg, if M is equal to 1 kg and Cp into delta T will give me what is the refrigeration effect per kg of air. So Cp is nothing but 1.003 and T3 is nothing but 268 and T2 is nothing but 156.9 Kelvin. This we have calculated in the previous slide. If I substitute these values, I will get what is the refrigeration effect produced. Now, what is my task? I have to find out what is the mass flow rate or mass circulated per minute. So, how to find that? So, this is the net refrigeration effect divided by the refrigeration effect per kg of air. That will give me what is the mass of air circulated per minute. So what is the refrigeration effect? It is 2000 kilojoule per minute divided by 1166 kilojoule per kg. So this kg will go up, kilojoule will cancel, I will get kg per minute, and if I simplify this, I will get 17.91 kg per minute. Now I know what is the mass flow rate. So once I know what is the mass flow rate, I can directly find out what is the compressor work, what is the expander work, what is the COP, and what is the power required. Now the compressor work. So for finding the compressor work, I need to find what is the temperature at 0.4. I know the inlet temperature for the compressor. If I know the temperature at the outlet of the compressor, I can find out what is the compressor work. So again I am using the same formula. T4 by T3 is equal to, what is T4 by T3? The exit temperature divided by the inlet temperature is equal to exit pressure by inlet pressure to the power of n minus 1 by n, and that is equal to 10 power 0.4 by 1.4, and it turned out to be, this is the value. I know what is a T3. T3 is a 268. Now if I multiply this at T3 268 with 1.92, I will get what is the value of T4, that is equal to 517.4. Now I know what is the temperature at inlet and exit of the compressor, temperature at the inlet and exit of the expander. So I can find out what is the work done. So what is the work done formula? It is also equal to mCp delta T, because they are following the isentropic process. The work done during the compression and work done during the expansion are given by mCp delta T. So what is the Cp value? Cp value is 1.003. Okay, Cp is 1.003 and M is 17.9, and T4 already we have calculated 517, T3 it is 268, and similarly if I substitute these values I will get what is the net work. It is not work done per kg, since we are multiplying with mass flow rate. I am getting the net work done by the on the compressor, the net work done on the compressor or work input to the compressor, and that is equal to this one. Now similarly for expander will produce some work. What is the work produced by the expander? Again it is equal to mCp delta T, T1 minus T2, highest temperature minus lowest temperature. So mCp, I have to put m here, m into Cp into T1 minus T2. So what is m? M is equal to 17.91. Cp is 1.003. T1 is 303 Kelvin, and T2 is equal to 156.9 Kelvin. Now if I substitute these values, I can find out what is the expander work, that is equal to 2628.42 kilojoule per minute. Now what is the net work done? So some work we are supplying to the cycle, and the cycle is giving some work in expander. So the net work is nothing but 4486.85. This is the work supplied minus work output of the expander will give what is the net work done in the cycle. So the difference is this one. Now I know what is the work done per cycle. What I need to know, if I know what is the refrigeration effect is also known. So the ratio of this, the refrigeration effect by work done per cycle, will give me the COP of the cycle. So the COP of the cycle is 2000 kilojoule per minute, the refrigeration effect, and the net work done, what is that? It is 18.58.43. So this is equal to 1.076. So this is the COP of the refrigerator. Now what is the power required? So the power required, I know what is the work supplied per minute. So if I know what is the work supplied per second, I can find out what is the power. So how to find out that one? 1858.5343 divided by 60, because 1 minute is equal to 60 seconds. If I divide that with 60, I will get a 30.97 kilowatt power. So this is the power required for producing this refrigeration effect. So this is the uh, end of the problem. So what we have seen, if the cycles, if the expansion and compression process are following the isentropic process, then the work done is equal to the heat absorbed minus heat rejected. If that is not a isentropic process or it is a polytropic process, then I have to find out the area under the graph for finding the what is the work done. So that is the difference between the polytropic process and isentropic process. With that, I am concluding for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.